Yes, I can hear you.
Okay,
Assalamu
thank
alaikum.
you.
Good afternoon.
Yeah, good afternoon. Okay, just waiting 1 minute, then we'll start. Okay, so I face some technical issue from my side. So I try to use join another link. We said that, so now I find out the proper link, then join. Okay, just you're waiting 1 minute, then we'll start. Okay, so we will start with this session. Okay, so first of all, welcome. Welcome to the another advanced online training program on research-based online training program. Okay. So in this, I hope I already completed my beginner's course for 7 days. We already know about that. Yep, yep. So you already know about the some basic function of Google Earth Engine. Okay, how it will work. So it's not the beginner's course. So we are just start the application. Okay, different types of remote sensing application, and this application may be research based. Okay, so we try to follow different types of scientific paper, and then further we try to apply or adopt this type of model using the code. Okay, and we try to suppose every section or every content we try to publish the scientific paper. Okay, so in this case you can easily choose your own study area. So after completing the session, suppose today I talk about that one topic, suppose Rusli model or other model, so you try to implement this type of model for your own study area, and further you try to publish the scientific paper. Okay, so this is our main goal, to publish the scientific paper is content. Okay, every content we try to publish and make the analysis. Okay, so first of all I try to discuss about our full course syllabus in the research based program. Okay, so which type or topic we try to cover. So let me share my screen, just a minute. Okay, can you see my screen? Is it visible? Can you see my screen now? Yeah.
Not yet.
Is it visible now? Can you see my screen now?
No, it's just showing your name, not yet displayed anything.
Why? Okay, just a minute. So anyone face this same problem?
I am seeing the screen. I can see the screen.
Yeah.
No, I am seeing the screen. I can see it.
Okay, so kindly you refresh your tab, then I hope it also okay. So I it also shared. Okay, I already shared my screen, and I also see it my another laptop. I also find out the screen. No problem. Yeah. Okay, so we continue. Yeah. So basically, this is our research-based training on GIS remote sensing with Google Earth Engine. So not only for the Google Earth Engine, we also help some other geospatial tool also, such as ArcMap or QGIS. We also take this type of help for the different types of analysis. Not all of using only for the Google Earth Engine, because all of analysis is not possible to use the Google Earth Engine. So we also learn some other tool also, such as QGIS, also ArcGIS or ArcMap. So this type of tool we also integrate with the Google Earth Engine and also complete our all of topic. Okay. So basically this is our total 14 days online training program. So each day, basically one day a week, we take the class. So for the Monday, okay, we take the class for this time. Okay, every day we try to meet the same time. Okay, no problem. And if you check this course content, so first of all, okay, so in this case, we try to add all of research-based content or research-based program. Suppose first time we discuss about the Rusli model for erosion risk mapping, how we can easily apply the Rusli model and how we can easily calculate the annual soil loss for any study area. Okay, for any study area, and how we can easily adapt our model. We also discuss about that. And if you check lot of paper only for the Rusli model, they use the Rusli model for soil loss estimation using the Rusli model and publish a lot of scientific paper we can easily publish. As well as we also discuss about the vegetation change detection. Okay, how we can easily use the suppose 20 years or more than 20 years, so historical data analysis. Okay, so how vegetation change year by year. So a lot of paper is available. So I also send you some reference paper also for every topic. So you also try, after completing the session, you also try to read this type of paper. Then you can also increase your knowledge about this type of topic. Okay. And we'll also discuss about the rainfall pattern analysis. So monthly, seasonal or annual. Then we talk about the land use land cover classification using machine learning. So I here all of you already complete my 7 days online training program. So I also discuss this topic also. But in this case, we also try to add the some other extra advanced topic for the machine learning. In this section we try to add, and then we try to make the land use land cover classification, and our main focus is the urban expansion. Okay, so how we can easily make the urban expansion, and lot of paper already published for the urban expansion or urban heat island or urban thermal field variance index. So we just simply combine, okay, suppose urban heat island or urban thermal field variance index or urban expansion. So this type of thing we also combine. Then LST and DVI time series chart for urban heat island. Okay, we try to identify for vegetation health and temperature trend for the urban versus rural zone area. We also try to identify. And satellite based aridity index. This is the one kind of drought assessment index. So how we can easily apply the aridity index and monitor the drought. We also discuss about that. Then LST monitoring using Landsat satellite imagery for the historical and identify for the hot spot for increasing the LST. We'll also discuss about that, as well as also linear regression and trend analysis, different types of climatic variable or bioclimate variable. So we'll also discuss about that, and also man candle and DVI trend analysis, how we can easily apply the man candle and project that detect the long-term greening and burning trends on the semi-arid region. Okay, and also VCI, TCI, VSI. So this type of index help you mainly working with drought monitoring. Okay, and also deforestation using machine learning, how we can get the deforestation using machine learning, such as illegal logging area, how we can easily detect using the different types of satellite images. We also discuss about that. And deforestation and agroforestation, we also discuss about that. And slope classification or area calculation, NDVI classification, raster extraction, and monitoring bioclimatic variable. Then it's lot of topic we try to discuss. Monthly evapotranspiration monitoring, and this type of topic we try to connect a paper. We try to connect a single scientific paper. Okay, so how to use the evapotranspiration, how I can use this evapotranspiration data and make a scientific paper. So that's why every content I will try to give you some reference scientific article, so then you can easily get the idea. This is the evapotranspiration, I can easily use it, and then further I make the analysis and publish the scientific paper. Okay, then soil salinity mapping, how we can easily do. Okay, soil salinity mapping and landslide susceptibility mapping. Okay, there are a lot of paper is available for the landslide using the different method. And flood mapping, there are a lot of paper. So in the 7 days previous 7 days training, I discussed about the flood mapping, but not talk about the flood damage assessment. Okay, so I can find out a lot of paper, they are only work for the damage assessment. Suppose how much cropland area is destroyed or how much urban is destroyed. for the flood. So this type of assessment we also discuss about in this section for flood mapping and damage assessment. And also we try to monitor the crop health using the agriculture productivity over a period of time, or agricultural land suitability analysis. Look, there are a lot of suitability we can easily do, but I tried, suppose I have a specific boundary. So in this boundary I want to find out which place have the more appropriate for the agricultural land. Okay, this type of things we also discuss. And same as livestock suitability. Okay, so there are a lot of paper you can easily find out the agricultural land suitability, livestock suitability, or this is very important for the future land use land cover prediction. Okay, we also try to discuss about that. Suppose I have the different years land use land cover classification map. So now I just simply add different types of independent and dependent variable. Further we try to apply the model, and then we predict the land use land cover classification for the future. As well as how we can also, using the same process, we can also predict for LST. Okay, for the future LST, or also urban thermal preference index. Okay, this type of things I'll try to discuss inshallah in this section. And barrel line and build up mapping. Okay, how we can easily use. And finally flood risk mapping. So this is our first batch, so that's why I try to add this type of topic. Further, if I find out more interesting topic, then I also try to including in this section. And this is our first batch in this. So every, suppose if I update my course syllabus for the future, then this type of material you also get the freely all time. Okay, if I update this material, suppose in the future I also add some new content or new topic in this syllabus, then all of you, because you already enroll this course, so all of you can easily get the this type of topic and get the freely. Okay, if I just add the more advanced topic future, okay, then you can easily get the freely all of content. And I can easily upload all of content in our Google Classroom. When I update this type of content, this material I can easily upload in our Google Classroom, then you can easily access from here. Okay, okay, so let me share my okay, let me open my slide. Okay, so let's wait and discuss one by one all of topic, then you can easily get the idea. So every day I try to complete the 2 topics, because here we find out the more than 30 topics. So if I just complete the every day, suppose 2 topic per day, then I hope it will be completed the 14 days. It will be completed the full syllabus. Okay. So today I discuss about that RUSLI model for erosion risk mapping, and also discuss about the NDVI change detection for forest degradation monitoring. Okay. So these 2 topics I try to discuss one by one, then you can easily get the idea. So first of all, we try to check some scientific paper about this type of topic. So let's go. So you can simply search your paper. Suppose, okay, let me check. So this is the one kind of paper, yeah. So this is the paper for NDVI Drape Vegetation Trend and Driving Factors in West African, this region. So in this paper, basically they are identify for vegetation trend, okay, and they are apply the model. It's called the man candles, okay, monotonic trend test. They are apply, and then they are identify for vegetation dynamics, okay, and further non-parametric they are used at the, okay. So I also send this type of paper also. You try to read, then you get the more better idea. So now suppose I want to apply this man candle test on my vegetation. So how I can do using Google Earth Engine and follow this type of material. So okay, so let me open my code editor, and when you face any question or any confusion, simply ask me. I try to give the answer all time, no problem. Okay, so first of all, let us discuss about the vegetation trend analysis. Okay. Okay. So first of all, we need to set our time period. Okay, suppose how much time you want to use for the vegetation trend analysis. Suppose I want to 1982, suppose 2025, or 1990 to 2025. Okay, so I want to use this data set from 1990 to 2025 and make the vegetation trend analysis. Okay, so for that, first of all, what I need? So first of all, I need the image collection. Okay, I need the image collection from 1990 to 2025. Okay, all of image I need for annual image collection. So how I can take the image collection? So in this case, we need to merge different Landsat satellite images. Suppose I need to merge Landsat 5, I need to merge Landsat 7, then Landsat 8, and Landsat 9. Okay, and then we can easily create the annual image collection from 1990 to 2025. Okay, so first of all, we need to create the image collection, and it's very important because when you work with historical data analysis, you need this type of annual image collection, not only for the vegetation trend. Suppose you want to make the LST monitoring from 1990 to 2025, then you need to create the image collection for annual image collection. Suppose you want to make the land use land cover classification, so then you also need to create the image collection from 1990 to 2025. So first of all, we discuss about that how we can easily create the image collection from 1990 to 2025. Then we discuss about the vegetation trend, how we can easily make the trend between this time period using the man candle test. So first of all, we simply import our study area, which area you want to work. Suppose in this case, I just choose one study area. Suppose, okay, let me open from asset tab. So I work with the mangrove forest, Sundarbans. So I simply import, and in the Sundarban mangrove forest, I want to identify vegetation trend analysis from 1990 to 2025. Okay, between this time period. So first of all, I need the annual image collection between this time period. So I simply choose my study area. I put the name, suppose AOI. And then I want to visualize my study area. So simple, just right here map dot add layer and display the AOI, and also focus the given study area map dot center object. Sorry, center object is AOI, zoom level was 10, and run the code. So now we find out this is my study area. So for this study area, I want to monitor vegetation trend between this time period. So first of all, I need the image collection between this time period 1990 to 2025. So now first of all, I need to merge Landsat 5, 7, 8, and 9. Okay, all of image collection I simply merge for my study area. And if you check, the Landsat 5, 7, 8, 9 have a common difference on their bands. So if you check, click on the browse data catalog and check the data set from Landsat. If you check, suppose Landsat 8 and 9, these two satellite images is the similar band combination. If you check, suppose Landsat 8, we try to use surface reflectance. And if you check the bands You can see SRB1, SRB2, SRB3. SRB1 is the coastal aerosol. SRB2 is the blue, then green, red, near infrared. Okay, and same sequence we also find out in the Landsat 9. Okay, just check the Landsat 9. Surface reflectance. And then check the SRB1 is the coastal aerosol. Okay, then blue, green, red, near infrared. So Landsat 8 and 9 are the similar sequence for the bands, but Landsat 7 is the different. If you check the Landsat 7, suppose Landsat 7 surface reflectance, we find out that you can see SRB1 is the blue band. Okay, so there is no coastal aerosol. SRB2 is the green band. SRB3 is the red band. So it's the another sequence. And if you check the Landsat 5, Landsat 5 and 7 are the similar sequence. If you check Landsat 5 surface reflectance, we find out the SRB1 is the blue, SRB2 is the green, red. So from here you can get the idea. Landsat 5 and 7 are the similar band combination, and also Landsat 8 and 9 are the similar. But when I combine, suppose I want to combine Landsat 5, 7, 8 and 9, then I need to make the same sequence, all of bands. Okay, so first of all I need to make the same sequence, because in this case I want to combine all of satellite images, Landsat 5, 7, 8, 9. But Landsat 5 and 7 similar, but Landsat 8 and 9 it's different. But when you merge Landsat 5, 7, 8, 9, you create the same sequence. Suppose B1 is the blue, B2 is the red, B3 is the green. Similar sequence, all of bands, because in this case I just simply merge all of image collection. So how I can make this similar sequence of band, all of image collection? So let's go ahead and discuss about that. So for that you can simply take a variable. Suppose I put the variable name is Landsat 5 bands. So this variable I simply write all of, store it. I just make a list and store it all of bands, and simply I take the another variable, suppose Landsat 7 bands. So in this variable I just simply store it all of bands of Landsat 7. Okay, and Landsat 5 and 7 are the similar, so I can simply write together, no problem. Suppose just I put here first band is the SRB1. Okay, then put the second band is the SRB2, then third band SRB3. It will be similar band, I simply write SRB4. Okay, and then I find out SRB5. Okay, and 6 is not available. Landsat 5 and 7, there is no band about the band 6, so we try to put here the SRB7. Okay, so we simply create Landsat 5 and 7, just put the Landsat band. So now I take the another variable. Suppose I put the variable name is the L5 names. Okay, L5 names. Okay, and also create the another variable in here, L7 names. So just I put the name. To take a variable L7 names and just store it, the bands. So at the same time I simply write the band name, because similar band name. So first SRB1, it's called the blue band. I put the blue. Then SRB2, it's called the green band, so I put here the green. Then SRB3, it's called the red band. Then SRB4, it's the near infrared band. SRB5, it's a short wave infrared 1 band. And SRB7, it's short wave infrared 2 band. So now Landsat 7 and Landsat 5 is done. I simply write the band name. So now we talk about the Landsat 8 and 9. So for the Landsat 8 and 9, so take a variable. Suppose I put the variable name is the L8 bands equal, and same take the another variable L9 bands equal, and I put the name. Okay, just put the band name for the Landsat 8 and 9 because similar band name I write the same at the same time. I simply write, suppose Landsat 8, I put the band name is that SRB2. In this case, you can see we simply skip one band. I skip the one band which is coastal aerosol because coastal aerosol is not available in my Landsat 5 and 7. But when I merge all of satellite image collection, I keep the same sequence, all of bands name. Okay, so for that I simply skip SRB1. So I start from SRB2. Then I put here SRB3. Then put here SRB4. Then SRB5. Okay, and also SRB6 because Landsat 8 and 9 SRB6 is available, and finally SRB7. So now just put the band name. So take a variable L8 names equal, and also take the another variable, suppose L9 names equal. So now define, so write at the same time. So just right here SRB2 is the blue. Okay, SRB3 is the green, SRB4 is the red, SRB5 is the near infrared, SRB6 is the short wave infrared 1, SRB7 is that short wave infrared 2. So now if you check all of bands, this line is the similar. Okay, you can say SR blue, green, red, near infrared, short wave. So Landsat 5, 7, 8 and 9, all the bands are similar. So now we can easily combine. Okay, so this is the first step. When you combine Landsat 5, 7, 8, 9, then we just keep the same sequence of band name. So in this case, blue, green, red, near infrared, short wave infrared 1, short wave infrared 2. I just put same sequence, all of bands name. Okay, so after completing these things, we just simply take our collection. Suppose I just take the collection for Landsat 9. First of all, I take the collection from Landsat 9. So same, just call the Landsat 9. I want to work surface reflectance. Just copy the snippet ID. Okay, and we already know about that, how we can easily filtering this type of Landsat image collection. I just put the same process. Take a variable, I put the variable suppose L9 and then paste here, and simply filtering. We already know about that filter bounds function, how it will be worked. So filter bounds with our study area, which is AOI. Okay, then put the filter date. Okay, so now I simply take the date from here. Suppose I take that whole time period. Okay, 2021 1031 to whole time period. I simply choose this is my start, and end I put the last time period 2025 0904. Just I copy and paste here, and then also put the filter metadata for filtering image property. So in this case we choose suppose cloud cover, and cloud, I just put the cloud cover. I put suppose cloud cover less than. So in this case, suppose when I put the less than 1, it creates some problem. This problem is that some year there is no image less than 1%. So then we find out the 0. Okay, it shows the 0. Suppose in year 1995 there is no image less than 1% for my study area, then it show a problem. It show the problem is that round figure 0, there is no image because less than 1% image is not available. So how I can handle this problem? So for that, you can simply increase the cloud level. Suppose I simply put the increase the cloud level less than 60, okay, or less than 80, okay. So now what happened? So now between this time period, less than 18, all of images stored in my collection in this variable storage. But when I increase the cloud level, some cloudy pixel appeared in my satellite images. So now this cloud I need to remove. So in the 7 days class, I also discussed about the cloud remover function. So how we can easily create the cloud remover function, and this function help you to remove the cloud. So this technique now we are using here, and further if I increase the cloud level and also apply the cloud remover function, then this cloud is not appeared in my satellite images. Okay, so this is the one way. Suppose now we need to create the cloud remover function, and this remover function we simply connect with the Landsat 9, Landsat 8, Landsat 7, and Landsat 5. Okay, so all of image collection is simply connect. So first of all, I simply create the collection. So just I create the another collection. Suppose now I create the collection for Landsat 8. So just change it. Suppose L8. L8, and I put the call the Landsat 8 image collection. So just click on here, back, and go to the Landsat 8. So click on the Landsat 8, and if you click on the surface reflectance for the Landsat 8, just copy the snippet ID of the Landsat 8 and paste here. Okay, so now also change the time period. This is the time period 2013 0318 to present time. Just paste here, and also you can see this is the time 2025 08 31. Okay, just I copy and paste here. Okay, and keep the less than 80% cloud cover. And finally, we also take the another, suppose Landsat 7 collection. Just I copy the same line of code, and this code we try to add with the Landsat 7. So put the L7, okay, and call the Landsat 7 image collection. So same process, just open the Landsat 7 and click on the surface reflectance. Copy the snippet ID and change it. So now also change the time period. Suppose I put the time period, this is the time period, start time. And this is the end time. Paste here. So now copy it again. So now we take the final image collection for Landsat 5. If you want, you can also merge the Landsat 4 or 1 to 5, easy, same process. So now I just take the another variable, suppose L5. Now just copy the snippet ID from the Landsat 5. Landsat 5. Surface reflectance. Copy this ID and then change it, snippet ID for Landsat 5. Okay, so now I put the time period from here. So this is my time period. It's available from 1984. I just paste here. and also 2012. And paste here. Okay, so now if you check, we simply import Landsat 897, as well as we also need to import the another thing, our bands. Okay, you can say I already put the bands and band name, so just put here dot select dot select function and put the Landsat 9 bands comma Landsat names. Okay, so now when I just put the sequence this way, so it take the last sequence, blue, green, red, green, infrared, short, movement. So it take the last sequence. So when I check the band name, so band name show blue, green, red, near infrared, not show the number B2, B3 not showing. Same process also apply for Landsat 8. Just I copy the same line of code and paste here, and I put it's a Landsat 8 band names and Landsat 8 names. Okay, then put the another for the Landsat 7. So put the L7 bands and L7 names. So same process for the Landsat 5. Just paste here. So put here the L5 bands and L5 names. Okay, so now we simply put the collection, but in this collection we put the less than 18% cloud. So when I display the image, we find out the some cloud. So now we create a cloud remover function. So this cloud remover function help me to remove all of cloud, okay, from my satellite images. Even if I increase the cloud level, suppose 80%, 90%, even 100% someplace, that there is no problem. But if I put the 1%, suppose for my study area, less than 1% image is not available for the any specific year, then it shows the 0. So further we try to keep the suppose 60% or 50% or 80%, and further we are just applying the cloud remover function. So then this type of cloud is not displayed in my imagery. We find out very neat and clean satellite imagery. And if you check all of image collection, Landsat 5, 7, 8, 9 have the similar band name for cloud remover. If you check, this band name is the QA pixel. If you check the band name, it's called the QA pixel. Okay, QA pixel. So this is a similar band and similar bit cloud and cloud shadow, bit 3 and bit 4, Landsat 5, Landsat 7, Landsat 8, Landsat 9, all image collection are the similar. So in this case, if I create a function and further this function, if I simply connect with my image collection, all of image collection, same function, then it will be okay, because all bands, all image collection, Landsat 5, then if you check suppose Landsat 7, Landsat 8, Landsat 9, all image collection are the similar band name and similar bit number. Suppose Landsat 8, check, we find out the similar band name and similar bit number. So that's why it easily work. Okay, you can see the QA pixel and you can see bit 3 and bit 4. Okay, bit number is similar. So now I create a one function. This function I simply connect Landsat 9, Landsat 8, Landsat 7 and Landsat 5. Then it's easily remove all of cloud and we find out the very neat and clean satellite images for every year. So let's go try to create a function. So I create a function in here. Suppose I put the name is that cloud remover function. Suppose cloud remover. So take a variable and just copy the, this is the band QA pixel. So in the 7 days beginners class, I also discussed about that, how we can easily work with the cloud remover function. Okay, so same things we are just apply. So take a variable, I put the variable name, suppose cloud remover. Okay, equal, create a function, I put the element name, suppose img, and then curly bracket. So in this curly bracket I just put what I need using this element. So first of all, take a variable, suppose QA, you can put any name as a variable, and put the element name and select the band of QA pixel. Okay, and now this band have a 2 bit. bit 3 and bit 4. So I simply use the this two bit 3 and bit 4. Suppose I just take a variable. Oh, sorry. So take the variable, suppose cloud shadow bit equal, put the bit number, cloud shadow bit number is the 4, just put the 4. Then take the another variable, suppose it's a cloud, so put the cloud bit, so 1 less than put the bit number, so bit number for 3. So we simply select the bit number 4 and 3. So for that, just take a variable, suppose max, and then this bit come from this band QA. Okay, this band basically stored in the QA. So I simply call the QA. So now this bit I want to connect with the bit 4 and bit 3. So put here the bit wise AND function. Yes, it also recorded. You can also get the recorded class also, no problem. So bitwise AND. So I simply call the bitwise AND because this band have a 2 bit if you check. So this type of things we also discussed in the beginners class 7 days. So I can explain. Suppose again the QA pixel. So this the 2 bit 3 and bit 4 I want to use cloud and cloud shadow. So for the connecting, just use here the bitwise AND function. Yes, any question please? Any question please? Yeah. Any question or any confusion, you can ask me anytime. Please.
Sorry for interruption. It's no question. Is it video is recording?
Yes. Yeah, recorded. You can, after the completing the live session, all of you can easily access the recorded class from our Google Classroom. Not only for the video class, all of practice code, everything, every slide or reference paper you can easily get. So now this is the band QA pixel. So bitwise AND. I just connect with this bit. So just paste here and set equal to 0 signal. Basically every bit we find out the 2 signals, 0 and 1. 0 indicating about that there is no cloud. And then put here the AND function. So AND, call the QA connecting with another bit, bitwise AND. This bit number is this cloud bit, just copy and set equal to 0 signal, which is indicating about the clear condition. So now what I return from this function? So I want to return this image update max with this condition, and this condition is stored in this variable max. Just copy and paste here. So now it's a cloud remover function we generate. So this function we can simply connect all of image collection. So how I can connect? Just copy the function variable name and then connect. Just paste here dot map and paste here. Also dot map and paste here. And also just dot map. Just I connect the cloud remover function with all of image collection, Landsat 5, 7, 8 and 9. Just paste here. So now what happened? So now if I increase the cloud level, this cloud is not appearing in my satellite images because I apply the cloud remover function. Okay. So this is the one way we can simply remove all of cloud. And if you just simply merge, suppose now we simply merge. So take a variable, just I make the combine all of image collection together. So for that, take a variable, suppose I put the variable name with the full collection equal to simply merge, suppose L9, then put here the merge function, put the L8, then it merge, then L7 merge, then L5. Okay, we simply merge the Landsat 9, 8, 7 and 5. And now I want to check how many image collection okay I have. So for that, just print this full collection and use the size function. So now it's computing how many images are available. Okay, we find out for our study area. So this is the total number of image collection. We find out 3,501 image collection. Okay, when I merge Landsat 9, Landsat 8, Landsat 7 and Landsat 5. Okay, suppose I just suppose I put the cloud level, I take suppose 50 or less than 50%, less than 50%. So first of all, we try lower cloud level. If I find out, suppose any year there is no image, suppose I find out 1 year it shows the zero means that there is no image, then we try to increase the cloud level. Okay, otherwise not need. Suppose some year less than 1% is not available, then we just increase the cloud level. Some year suppose less than 10% is not available, then we simply increase. So now if you check how many images are available, so we find out that 2809 images after make the combination Landsat 9, 8, 7 and 5. So this is my full image collection. Okay, we find out. But what is my target? My target is that I want to create the annual image collection from 1980 to 2025. Okay, annual image collection. And further I want to check the vegetation trend analysis. Okay, so for annual image collection, we create a function. Suppose I create a function. Function. So this function basically help you annually. Suppose 1990, it's find out suppose 5 images. So then just use the 5 images and create the median composite. Okay, suppose similar, suppose I find out the 1991, it find out suppose 4 images or 3 images. So these 3 images combine and create the median composite. Okay, so I create a function. So this function filter yearly. Suppose from 2809 images, it filter yearly. Okay, suppose 1990, it's find out 5 images and create the median composite. 1991, it's find out the 3 images and create the median composite, and up to 2025. Okay, so now how I can filter? So I have a collection. So this collection I want to filter annually. So this is my target. I have a collection. This collection I want to filter into annual image collection. So for that, first of all, you need to define your observation time period. So let's go try to take a variable and define observation time period. So take a variable. Suppose I put the variable name is start year equal. So I define the time. Suppose it will be start from 1990. So this is my start year. Take the another variable. Suppose end year. I put the time, suppose 2025. Okay, so I define my observation time. This observation time, every year I need images from this collection, and further I create the median composite. So this is my final argument, and these things I just create a function. Okay, for this I create a function. This function filter this image collection every year between the time period. Okay, and create the median composite. So let's go try to create a function. Okay, suppose this is the image collection. Okay, so this is the image collection 2809. Okay, these images or this image collection you want to convert into we find out that how much year? 36 years. Yeah, 36 years. Okay, so this 2809 image collection I want to convert into 36 years between 1990 to 2025. Okay, so this is my ultimate goal. So I have this image collection. This image collection I will convert into total 36 years. To 36 years image collection. So how I can do it? So for that we use a function. This function called, I will just show you the function from the docs tab. EE dot image collection from images. So we need to use this function. Okay, this is the function. So EE.image collection from images. Suppose I have a image collection. So from this image collection, I create the another image collection. So I have a image collection 2809 image collection. Okay. So this image collection I need to convert 36 years image collection. So for that I need to use the function ee.image collection from images. So I have some images, 2809 images. I want to convert another image collection, 36 years image collection. So let's go try to create this image collection. So take a variable. I put the variable name, suppose annual collection. Okay, and now we define this function ee.image collection dot from images. So this function, because I have image collect, I have some images, so these images I want to convert into other collection, so let's use this function. So in this function I create a function. So this function help me to filter every year from 1992 to 2025. Every year is filtering. Suppose 1990 it find out the 5 images and create the median composite. 1991 it find out the 3 images and create the median composite. So for filtering I create a function. So just we create a function. Suppose take the variable name, put the function keyword and put the element name, suppose y. I put the y. Okay, so in this case this y element indicating about the year. Suppose every year just come in this element or just put in this element and filter and find out images and create the median composite. So just I create a function and put the element name is the y, and what is my argument? So my argument is that I want to filter this image collection annually or year by year. Suppose 1990 all of image I want to filter, 1991 all of image I want to filter, 2025 up to 2025 all of image I want to filter and create the median composite. So for that create a variable, suppose annual equal, and I already have the image collection, full image collection, just I call it because it stored 2809 images. Just call and paste here. So these things I want to filter. And how I can filter? I want to filter year by year. Suppose 1990, 1991, 1992 up to 2025, all of year I want to filter. So for that we simply use a function. It's called the ee dot filter dot calendar range. Okay, so this range will be year by year. So put here the y element and put the unit is the year. Okay, so this is the full collection. I just filter year by year, and after filtering what I do, I just create dot median composite. Okay, and further I just clip with my study area, which is AOI. So in this case, if you check what I do, I again explain. So I create a function. So this function help me just one by one this year come in this function and filter yearly. Suppose first year 1990 I find out the 5 images, it create the median composite. Then up to 2025 all of images and clip with our study area. So now how I can define the year? Okay, so for that we create a list. We just create a list all of years. So take a variable. Suppose I put the variable name is the years. So this variable I stored all of years between 1992 to 2025 all of years. So put here ee dot list dot sequence and put the time start year and define the end year. So just I simply make the list all of years. So now when I connect the list with my function, what happened? One by one, here just filter and create the median composite. So let's go try to print and check what happened. Just I comment all of line together and I want to print. So I will just print the list of years and run the code. If you check, we find the 36 and basically you can see 1992 up to 2025. Okay, this is the list of serial of years. So now we try to just connect this function. So, and before that, we also just return what I return from this function. So I want to return annual, this variable annual, set yearly. So set year and put here the y element. Okay. So now it's created a function. So in this function, I simply connect with my list of year. So just I call the years, copy the variable and connect with this function, help of map function. Just put the map, start the bracket and also close the bracket. Okay, so now this is the function. It's help you to compute all of yearly median composite images. So if you check, just print the annual collection and run the code. We make a mistake in here. This mistake is that QA pixel did not match any band in our list. Okay, so because we are not defined the QA pixel band in our list, so we try to put the QA pixel. Okay, because all image collection are the similar same band name. So just I put all of the new this band QA pixel because it's similar. So just write here this QA pixel. So now run the code. So now if you check 36 element, click on here, you can see it show the 7 bands. So all of year we find out the total 7 bands. So this is the image for 1990. Or click on here, this is the image for 1991 and up to 2025. Okay, we find out the image. It's the annual median composite image. So now I want to suppose display the image. Okay, I want to display the image. So for that, if you want, you can simply use here the map dot add layer and call the annual collection. And in the annual collection, suppose I want to display all of bands. So for that, just apply the 2bands function, 2 bands, and run the code. So now in this layer, it added all of bands. We can easily add it in our map. If you check, suppose, so this is the image. So now just click on here, and you can see 0 blue, 0 0 0 red. So if you click on here, you can see 0 basically first image, first year 1990. Okay, you can see. Then 1 mainly 1991. Then 2 1993. And then up to you can see total 35 or 36. Okay, 35 mainly 2025. Suppose I want to display the image in 1990. So put the suppose red band, then put the red green and put the blue band, and stressing suppose 98% I keep. And another problem you can see, it show the digital number. Okay, it show the digital number. So this digital number we need to convert into reflectance value. Okay, so I will show you after some time how we can do it. So now we find out the image in 1990. This is the image, but this digital number we need to convert into surface reflectance value. So how I can do it for converting? So I will show you that, then explain again. Just a minute. So if you check the image collection in the Landsat surface reflectance, they provide the some scale value and also give the some offset value. So basically when I use this type of scale value and offset value, this reflectance value convert into this digital number, convert into reflectance value. So how I can converting or scaling? Okay, so let's go try to add the scaling and then rescale our image, then can get the idea. And if you check the all of bands are the similar scale and similar offset. Okay, all of bands for the Landsat 7, Landsat 8, Landsat 5 are the similar scale and similar offset value. So that's why I can simply use the one function. This function I can easily apply all of image collection. So check the Landsat 7 for the surface reflectance are the similar. Scale value and offset value are the similar. All the bands, but one bands have a problem. This band called the thermal band. If you check the thermal band, this is the STB6. Okay, this is the band name STB6 thermal band. And if you check the Landsat 8 and 9, this thermal band name is the STB10. STB10. This name is the STB10. So this is the only one band difference, STB10 and STB6. Basically Landsat 5 and 7, the thermal band name is STB6, and Landsat 8 and 9, the thermal band name is the STB10. Okay, so you can simply define it, because and if you check for the thermal band have the another scale value and offset value. You can see thermal band, this is the scale value and this is the offset value, another value. But all of optical bands are the similar scale and offset value. Only for the thermal band have the another scale and offset value. And scale and offset value are the similar all for the Landsat 8 and 9 also for the thermal band. Okay, so let's go try to rescaling our data. So this process basically it show the digital number. Okay, it's not the reflectance value. So we need the reflectance value in the remote sensing. So that's why we need to convert digital number to reflectance value. Use of scale and use of offset. So let's go try to do it. So I create another function in here. Again, we define the band name. Suppose this band Landsat 5 and Landsat 7. This band is the STB6. Okay, and for the Landsat 8 and Landsat 9, this band name is STB10. Okay, STB10. Basically this thermal band is neat when you work with the land surface temperature. Suppose you want to historical land surface temperature or urbanite island or anomal thermal field variance index, so then we need this type of band. Okay, so I simply put the STB6 for the Landsat 5 and 7, STB10 for the Landsat 8 and 9, but I keep the same name. Okay, for all of image. So I put the name, I put the name, suppose BT. Okay, or brightness time, I put the BT. Okay, so I put you can see our last line name are the similar. Okay, for the Landsat 8, 9, 7, 5. So this is the main condition when you merge all of image collection together, otherwise it not work. Okay, so I put the BT. Okay, but this BT it's come from STB10, and also this BT it's come from STB6, because Landsat 5 and 7 STB6 is the thermal band, and for the Landsat 8 and 9 STB10 is the thermal band. Okay, so now I want to rescaling Landsat digital number to reflectance value. So we try to rescaling or applying a scale factor. So take a variable. Suppose I create a function. I put the function variable name. Suppose apply scale factors. Okay, and create the function keyword. Put the element name. Suppose img. Okay, and then I put here my argument. So what is my argument? My first argument, I have the bands blue, green, red, near infrared, short wave infrared. So this type of optical bands are the similar scale. Okay, similar scale, blue, green, red, near infrared, short wave infrared, and it too similar scale value and similar offset value we find out for this type of optical bands. But only for the thermal bands, it's the different scale. So we create a function. Suppose I create a function is that optical bands and call the element and select all of optical bands and store it in a list. I simply call all of optical bands. Just call. Yeah, just copy. Okay, kindly mute. So just paste here. So now you can see I simply select only for the optical bands blue, green, red, near infrared, short wave infrared into, and then I simply multiply. Put here multiply with the scale value. Okay, so this is my scale value. Just I copy and then paste here, and then also add with offset value. So what is the offset? This is the offset value. Just I copy. So now I rescaling all of optical bands. Okay, and now I take another variable and rescaling the BT or thermal band. So for that, take a variable. Suppose I put the variable as thermal band, call the element img and select the thermal band. So this band name is, I put the name is the BT. So I put here the BT and then multiply with our scale value. What is the scale? Scale for this is the scale for thermal band. Just I copy and paste and add the offset value. So this is the offset value 149. Just I copy and paste here. Okay, so I can we simply define the two different variable and rescaling optical band and thermal band. So now we simply what I return from here, just I put here the return. Okay, just create a problem. Yeah. So we return what we return. I want to return this element img, add bands with optical bands. Just I copy and apply null and also open the true. Okay, and same process, add bands, call the thermal band, put here the null and true. So now this is the function. Okay, this function help me convert digital number into reflectance value. So I want to use it. Just I copy and use in my every collection I want to use. So I was just use here the dot map function and apply. Okay, and also just put here the dot map function and I want to apply. So I want to put here dot map function and I want to apply. So I put here the dot map function and apply. Okay, So now every image collection we can simply rescaling our scale factor. Okay, so now if I check the run and check the result again, okay, so now if you check, suppose I want to display the map in year of 2025. So for the 25 we just simply choose the 35 serial. Suppose 35 we simply choose red band, and also for the red then green I select from 35 sequence. So 35 green and 35 blue, then we can get the image in year of 2025. So 35 blue, okay, red green blue, and stress is of 98%, and apply. So now we find out this type of imagery in year of 2025. Here we find out this type of imagery. Okay. But this is the not proper way to display the image. So we can also display the image in that another way. So I'll show you this process also. So when I put the two bands, what happened? You can see I just use the two bands function. So this function helped me to display all of bands. Okay, all of bands for the 36 year images, all of bands it display. Okay, so you can see from 0 to total 35, mainly 36 years image, all of bands it display. So you can see 0 blue, 0 green, 0 red, 0 near, 0 short wave infrared, 0 short wave infrared, 0 QA pixel, 0 bt. So this is the 0 serial for 1990. Then this is the one serial all of bands for 1991, then 1992. So all of serial we can easily get in here from here to display the images. Suppose if you want, you can also display the image for another study area. So how I can do it? Simply change the study area. Suppose I need the image for another area, so simply import your shape file. Suppose I want to work for the Dhaka city, then we can easily get the better idea for change. Suppose just import the Dhaka city boundary. Why it's taking a lot of time? Okay, done. So I simply remove the previous AOI and I put the new AOI. So AOI and run the code. So now we can get the image for in the Dhaka city boundary. Okay, it's loading. I think some networking issue, that's why it takes some time. Suppose now I want to display the Dhaka city boundary. So I want to display the image, suppose in 1990. Suppose I put here the red, then put here the green, and put here the blue. 0 mean 1990. Okay. It's tracing 98%. So you can see now it shows the reflectance value range. Just I apply. So now you find out this type of images, image collection. Or if you want, you can also display the vegetation. So then we try to apply the another band combination. Suppose near infrared 0, near infrared, then red and blue, staging 98%. Then apply. So now we find out this type of mapping. Okay, red color indicating about the vegetation area. This type of red color. Just I import the visualization import. So after importing, just I copy the visualization and paste after the layer name. So this is my layer name. Just I paste and I put the suppose layer name 90. So now run the code. So now this visualization is set with my map. Okay, so now we add the another visualization, suppose another year, suppose 2025. I want to add this layer. So for the 2025 we can, how we can add? So simply go to the 35 near, then 35 red, 35 red, near infrared red, and 35 blue, 35 blue, stressing 98%. Okay, further just apply and import, and I want to add the another layer. So just copy the same line of code, just take copy and paste here. Simply change the visualization parameter. So just I copy this new parameter and paste here. So now I put it's a year of 2025 and run the code. So now we add the two time period. Same process, you can also apply and add the other years easily. Same process, just apply and add the others years image. It's loading. So again, we find out this type of visualization. This is the 2025. This is the 1990. So you can see the difference between 1990 and 2025. Okay, you can see. So now further, when I discuss about the land use land cover, so then we also try to use this type of image. Okay, basically this image, annual image collection is very helpful for the different types of work. So now we have total 36 year image collection. Okay, 36 years annual image collection we have. So now we can easily use it for NDVI trend analysis. We can easily use it for land use land cover change detection analysis. We can easily use it for different types of historical data analysis. You can easily use. Okay, you can see. So this is the 1990. We find out the lot of water body area, lot of vegetation area, lot of agricultural land area or cropland area. We can find out very less. You can see very less built up area. We find out, and but you can see 2025. We find out that this type of condition. So now suppose I want to use this, suppose for the Dhaka city, I want to identify vegetation trend. Okay. So let's go and show the example for this trend, but you can also apply it for any other study area, same process. Okay. Then we try to check which place vegetation loss, which place decrease the vegetation. So this type of analysis we will do for this study area. And you can see lot of water bodies decrease. So this type of black color indicating about the water body, this type of black color. Okay, when I use the visualization, then you find out this type of black color is the water body. But 2025 we find out this is the water body, very less water body, and also increase lot of build up. Okay, so let's now we try to, okay, so this is the one process to add the image visualization. So just use the two bands and import your visualization. Okay, and we can easily visualize any other years or annual image collection. But if you want, you can also visualize the image another way. Suppose I just display the another way. Suppose take a variable. Suppose I need the image. Suppose 9090 or 9090. Okay, I need the image. So this image I need to filter from the annual collection, because if you check in the annual collection, total 36 years image collection. So I want to filter. So just I copy the annual collection. So from the annual collection, I want to filter for 9090. So put here the filter. So how I can filter? Earth engine dot filter dot equal. Okay, so what's equal what? So if you check, suppose property year, then 990. So I want to filter year, comma 990. Okay, so now what happened? Just I simply filter year equal to 990, and I create some mosaic. Okay, so now display, just put here map dot add layer and 990. Okay, sorry, image, this variable image 990, and run the code. So now this is another way to add the image. So now further I can use the image and make the land use land cover classification, because this 990 image is stored in this variable, but previous time you can see it's not stored. Okay, what is the, oh sorry, this annual collection I want to filter. So now run the code, because this annual collection is stored all of annual images from 1990 to 2025. So just I simply call the filter, and how I can filter, I want to filter year equal to 1990. So now this variable is stored 1990 image. Okay, annual image, annual median composite image. So now this variable is stored this image. So now I can use the variable and make the land use land cover classification in 1990. I can easily create the different types of indices, suppose NDVI, NDWI, or anything, because this image is stored in this variable. Suppose I need the another image, just I copy the same line of code and then paste here. So I need the image, suppose 2000. Same process, just year equal to put here the 2000, and then I want to display, because now this 2000 image is stored in this variable image 2000. So now we can easily get the image for 2000. Okay, let me add the color. So just click on here, then we can easily get, suppose band name red, green, and put here the blue. Okay, and still about 98%. Apply and import. So further just copy this visualization parameter and paste after the object, and I put the layer name, suppose 90 image. Okay, you can put any name. So now run the code again. So now it will be load for 2000. Okay, so I want to add suppose another year. Just I copy same line of code. Suppose I need the image in 2010, and I set year equal to 2010. Okay, and then I want to display image 2010 and paste here. So let me add the color for this. So I put at suppose RGB, red, green, and blue. Stressing suppose 98%, and apply. Then import. Then click on the visualization parameter. So this thing simply connect after the object name, and then put the layer name. I put the layer name, it's a 2010 image, or you can put any name as a layer. So suppose then I need the layer another, suppose 2020. So same process, just I copy same line of code and paste here. So put suppose year of 2020, then set equal to year of 2020. Okay, and then I want to display. So just I copy and paste here. So I add the visualization after adding the layer. So just I put the empty and run the code. Change the layer name also. It's a 2020. Okay, so let's add in here. Suppose red, green, and blue. Import, copy. So now, okay, add all of those. So now run the code. So now we can easily get this type of image. So further we can easily use this type of image. We can easily make the land use land cover classification or anything we can do. And it also help you a lot of time when you work with. Suppose I want to make the time series chart of NDVI from 1990 to 2025, or I want to create suppose LST mapping. So lot of time. Okay, so in this session lot of time I use the same code, and previous time I just show you the work, because I hope you can also get the idea how we can easily convert, okay, and how we can easily merge Landsat 5, 7, 8, 9 image collection. So this same process you can also apply also for Sentinel-2. So it's also your homework or also assignment I also keep. Suppose for the Sentinel-2 surface reflectance, you try to create the annual image from 2017 to 2025. Okay, so 2017 to 2025 you try to create annual images, use the Sentinel-2 surface reflectance image collection. Okay, so for that not need to merge, because it's only available for the Sentinel-2 SR. Okay, but Landsat have Landsat 5, 7, 8, 9. So that's the reason we can just make the similar band combination, okay, all of Landsat, as well as we can also create the merge. We also merge. Okay, this portion is not need when you work with Sentinel-2, because Sentinel-2 just stored all of image in the one image collection. So you also try for the Sentinel-2 surface reflectance, try to create annual image collection 2017 to 2025. Okay, and then also display the result. Okay, so anyone any question you can ask me for the annual image collection. Yes, please. Please.
Yes, thank you very, very much. Now, if you have the image collections just up to 2025, and you've created LST or surface temperature or land use and cover change, can you now use that result, say, to predict what the land cover change will be, say, up to 2030? Can we do that?
Yes. So I'll also show you that all of process step by step. So how we can easily create this type of land use land cover, and we try to predict. Okay. So prediction, I try to use some model as well as also show you the Google Earth Engine help of random forest algorithm, how we can easily predict for the future land use land cover classification, and also use some model. Okay, so it also show you that, no problem, it also cover for the future. Suppose I have the image collection, I suppose I create 2000 2010 2000, or create suppose 2000, then 2010 2020, and then I just put the 2030 predict. Okay, after that I can also predict suppose 2040. Okay, suppose I have the land use land cover map for 2000 2010 2020, then we can easily predict 2030 and 40. But now this process you can apply and easily get this type of result. Okay, this type of image we can easily get. So further we can simply use this type of annual image collection and make the land use land cover classification. Further, this type of land use land cover data we can simply input in our model in Google Earth Engine, and also use some other plugin model, then we try to predict. Okay, so inshallah these things will be completed, no problem. Yes, please.
Also, sometimes when we are doing these things, you can check when you want to check for your image, total image collection is study area, for instance, for Landsat 8, it becomes 0. And also when you want to compete for the cloud cover, say 80%, sometimes even 90%, it is 0. So what do we do in those cases?
Then you try to increase the time expansion, increase the time period. Okay, increase the time period, then it will be okay, no problem. Okay, suppose I check it, I increase the cloud level 90%, but there is no image. So further we simply increase the time duration or observation time, simply increased. Then I hope we also get the images, because some place there is no image, so then we face this type of problem. Okay, so I hope you got the idea about that for image collection. So now we talk about that how we can easily apply the your trend analysis. Okay, for the trend analysis, okay, let me open, and I want to make the trend analysis for this same study area, and we can apply the two types of trend analysis. One is the linear regression, another is the your man candle. Okay, two example I will show you that, because in this paper they are using the man candle or MK trend test, and further they are make the analysis, and some paper they are also use the linear regression, basically NDVI equal to y equal to mx plus c. Okay, so let's try to explain, then you can get the idea. So now what is my ultimate goal? I want to NDVI or NDVI trend from annual collection. So I have already make the annual collection, total 36 years. Okay, so first step, we add a numeric year band to each annual images, which is the first step. So what is the first step for that? I also write the comment, so that's why when you read the code you can easily get the idea. So first step, we need to add a numeric year band. Okay, numeric year band, and we can also say that it's a time, or we need to add the time band, the time to is annual image. So this is the first step. Add a numeric year band or time band to each annual image. So we already create the image collection, annual image collection. You can check. We already create the annual image collection. Total 36 years annual image collection. But if you check, there is no band. You can check. We can find out only for this type of band, but there is no band about the NDVI. Okay, you can see there is no band about NDVI. So first step, I need to create the band of NDVI because I want to make the NDVI trend analysis, okay, using annual image collection. So now I need to create the NDVI band, okay. So how I can create the band? So let's go ahead to discuss about that. And this band I need to connect with my each year images every year. Suppose in 1990, this image I create a band, new band, NDVI. Then 1991 I create the another band, NDVI, and up to 2025. Okay, up to 2025. So all of annual images I just add the new band of NDVI because I want to make the trend analysis of NDVI. So let's go try to add. So how I can create the band? So I write the code in here. So create the band. So for creating the band, first of all, just take a variable. I put the variable name, suppose add band equal. So add band equal, then put the function keyword, and put the element name, suppose img. So I just use this element, and what is my argument? My argument is that I compute NDVI, and this NDVI I want to connect with all of annual images. Okay, take a variable, suppose NDVI, call the img, and put here normalized difference between two band, okay, near infrared band and red band. So near, NIR, near, I use the same band name, you can see NIR, near, okay, because I already rename all of band name, so I just put the same band name, otherwise it not work. So I put the NIR, near, and also put here the RED, red, okay. So I define compute, and I put the name, I put the rename as a NDVI, and every function all time we need to return. So actually what I get from this function, it define the return function. So put the return, so return this image, add bands, return this element, add bands, and put the this variable NDVI. So now this is my function, this function compute NDVI. This function I need to connect with my annual image collection. So annual image collection, where is it? You can check the annual image collection, annual image collection, this one, okay, it is stored, annual image collection, okay, annual image collection, it is stored. So now I want to connect this function with this annual image collection. So for that, just take a variable, you can put any name. I put the variable name, suppose I put the name, take a variable, suppose put the variable name is that annual NDVI collection, okay, it's this type of name. So now call this annual collection, just I call, and I want to connect the function. So just put here the map function and call the function variable name. So my function variable name is add band. Just I copy the variable name and connecting with my where is it? This one, yeah. Just simply connect. So now what happened after connecting the band? If you just print, suppose print this annual and then check the result and run the code. So now if you check, it create the another collection, and if you check every image or every year, it create the new bands of NDVI. Okay, every year from 1990 to 2025, we are just get the result of NDVI. So this is the process. Suppose you want to work with another indices, because you already know about that different types of indices, we can easily connect this process. Simply create the another band, simply connect. Okay, with that, suppose I have to create another band, take a variable, suppose NDWI, call the element img. So normalized difference between two band, which is green, and another is the near infrared. Okay, so I define green and near infrared, and I rename it as a NDWI. So now just put here add bands and call the bands NDWI and run the code. So now every annual images add the new band, and this band name is NDWI. Okay, if you check, just click on here. So you can see year of 1990, it's added the new band of NDWI. Okay, all of images added the new band of NDWI. Okay, so this is the way to create the band and connect with your annual image collection, because I want to create the annual NDVI trend. So this is my goal. So for that, I simply create the band of NDVI and connect. Okay, so now, so we find out also. So annual NDVI, this, suppose this one I want to add the layer, and this type of things I simply use at that false. So when I put the false, what happened? This type of layer is not loaded, is not opening. So I put the false, because now it's not neat. Just I simply put the false, because when I put the false, this type of layer is not opening in my map. So put the false. Okay, it's not neat now. False. So I want to add the layer. I just add the layer. Suppose map dot add layer. I call the NDVI collection, but I want to add the band only for the NDVI. So put here the select and put the band name NDVI and apply the two bands function. We already use this function, two bands. Basically it display the bands, but now I want to display only for the NDVI. Two bands, when I apply, it just show the only for the NDVI from all of year, from 1990 to 2025. Okay, now let's run the code and check what happened. Okay, which one? Okay, let me check. Okay, I'll put it's also false. It's not need to display now. Okay, so now we find out only for the two layer. Okay, so I think this layer. So now if you check, just click on here. So you can see, suppose I want to display only for the one band. So 0 mainly 1990 and up to 2025. So we can easily display all of yearly NDVI. Okay, every year. So this is the result for 1990. I want to add the NDVI, just STC 98%. So I want to display the NDVI map. Suppose water body display as a blue color, greater than it shows suppose this type of color, and show the green color. Okay, so now it display the map of NDVI in 90, 90 we find out this map. So we find out this type of NDVI map 90. Okay, you can see this the vegetation. Green is the indicator of the vegetation. Okay, so I just import and put the layer name. Just I copy and then just connect after the object name. So after that just paste here and put the, it's a NDVI 90. So now it will be save the color, okay, with visualizer. So now when we add the NDVI map, suppose in 2025. Okay, so I want to use the same color, so just click on the pen sign and copy the color, because I want to add the same color for 2025 and just stressing again 98%. Okay, then simply apply. Okay, and then import. So now further, okay, so simply add the another layer. So just I copy the same line of code and paste, and then call the visualization parameter which I imported, this one, for the 2025. So where is it? This one, and put the layer name, suppose 90 NDVI 2025. So now run the code. So now you can easily combine comparison between the NDVI 1990 or 2025, or you can also export this type of NDVI map also. Okay, further you can also use the arc map to display your research paper, other things. Okay, exporting. So now again, so you find out this type of map. And if you want, you can also apply the NDVI change detection. Okay, so you can see this is the result for NDVI. You find out the in year of 2025. Okay, green color indicating about the vegetation. Okay, this type of green color, and this is the result for 1990. You can see. So further you can simply, lot of things you can easily do from here. Okay, for the NDVI change detection, compute the NDVI change area, lot of things. Okay, you can easily do from this type of result. You can see. Okay, so we find out that lot of vegetation is decreased between this time period. Okay, so let's go. This is the process. Or if you want, you can also export this type of every year NDVI map. Further, you can also help of ArcMap or QGIS software to produce the map. Okay. Okay, so this is the process. We simply connect the NDVI band with our annual image collection, and further we also display the NDVI result. So now my target is that I want to NDVI trend analysis for my time period. So for that first step, we need to create the band. We need to create the time band. Okay, add a numeric time band with its annual images. So for that, just take a variable. I put the variable name, suppose with time equal, just create a function. Okay, just create a function. This function help me to compute the time band or year band for every annual image collection. Okay, so now just create a function. function. So in this function, I put the element suppose img and put my curly bracket. In this curly bracket, I put my argument. What is my argument? So my argument is that I want to create the new band of year for every annual images. So take a variable, suppose y, and I put here is a numeric, so numeric or number, put here e dot number, and this number, it's come from the element basically every year or every annual image, and it get the year because we already set, you can see in our annual collection we already set, you can check this one, I already set the year property, you can see year. Okay, so same things as this image, every annual image, so every annual image just put in this function and get the time or get the year from this year keyword, because you can see year keyword is stated the year 1990. Okay, just I simply define using a function again, and then take another variable, suppose t equal, so we create the band. Okay, so it's a numeric value, so this numeric value we need to convert into band. So for converting the band, we just use the help of e dot image dot constant, this function we simply define the y. Okay, so this numeric number we simply store it, help of image dot constant, just call the y and paste here. Okay, just store it in here. And now this, it's not only for the, it's just work only for the integer, because you can see 1990 is an integer value. So I want to, when I create the image, so then some floating number or floating pixel number is also available. So for that, use the float function, otherwise it shows some problem. So just put the float, and then I rename it. I put the rename the band name, rename this band name as a time. Okay, so we can get the idea how we can create this function. And every function, what I return, so what I return from this function, I want to return this variable work as a band. So just simply put here the return this element, add bands with t. Okay, this variable t, and then we set, so simply set the time, so put here the system time start. Okay, so this function, it set the time band from my system time start. System time start basically which time it will be start, 1990. So it will start from 1990. It's create the time band from 1990. So we define it system time start, these things. And also we also define the format. Okay, date format. Suppose I put the format, so put here comma sign and put the date format. So put here e dot date dot from ymd. Okay, year, month, day. Then define the date format. Suppose year, I put the first month, first date. Okay, and also apply the another function, it's called the millisecond. So put here the millisecond. Okay, millisecond. So this function is simply defined. So now what happened? So this my function. So this function, every annual NDVI collection just come each year 1990, 1991, 1992, 92 and create the time band. Okay, create the time band. So this is my ultimate goal. So now I want to connect with my annual NDVI collection. So you can see I already create a variable which is stored the annual NDVI collection. Okay, not only for the NDVI, basically it is stored all of other band also, but our main focus for NDVI. So just I copy the NDVI collection and connecting with our function using the map function. Just put here the map function, put the parenthesis and also put the parenthesis. So now what happened? So this variable stored the NDVI image collection every year 1992 2025. So now one by one year come in this function and create the time band. Okay, create the time band. So that the reason is simply use it. So now if you want just simply print, suppose I want to print this with time, then it display the one band for time. So if you check, where is it? Click on here. We find out the feature. You can see 11 bands. So now we try to check all of bands. We find out a new band time. Okay. So why I create it? Because we are just apply the linear regression. Okay. So that's the reason we simply create this band, time band. It's need when we apply the linear regression. So linear regression basically, if I just explain short time, suppose if I just take a suppose NDVI equal suppose A plus B multiply ER. Okay, so in this case you can check, suppose we just compare this equation, y equal mx, or suppose mx plus c, same. Okay, or you can put the c plus mx, same. So now we are just applying this type of formula in here. So here basically b is slope. So b, suppose this b, or from the m is the slope. Here we find out the b is the slope. So b is the b equal, we can simply write here, it's a slope per year. Okay, b is the slope per year, and year, it's a year basically y equal to, this is the x. Okay, x, and b is the slope. Okay, and c is the intercept value. So now in the linear regression, we just identify the time and NDVI band and apply a function linear fit. Okay, so let me show you the what is the linear fit, then you can get the idea. So let me open the function in the docs tab. So I simply search here linear fit. Linear fit, yeah, so this is the function linear fit. So if you check the linear fit, return a reducer that compute the slope. Okay, so now I need the slope, I need to compute the slope, and offset for weighted linear regression of 2 inputs, and the inputs are expected the x data allowed by y data, and where applicable output name is the scale and offset. Okay, so we find out 2 output, scale and offset, and from this linear fit function it compute the slope and offset for a weighted linear regression for 2 inputs. So in this time my 2 input is the NDVI and another is for time. Okay, I want to use it as an input, so time and NDVI. So then it compute the linear equation equal to mx plus c and compute the slope and offset. So from the slope we can easily get the idea where is the high vegetation loss, where is the low vegetation loss. This type of things we can easily get the idea. So let's go try to apply this function and check what happened. So from this function you can get the slope value, you can find out the slope. So now we are applying the trend. So just take a variable, suppose trend, and call this with time, because it is stored the time band, okay, as well as also NDVI band. This variable is stored, we already check it, you can check it is stored the NDVI and also time. This is the NDVI and time. Suppose you want to make the analysis for NDWI and time, same process. Suppose you want to identify for water, where is the water, linear regression, help of linear regression, you want to identify water changes. Okay, where is the water change, where is the water not change, or increase, where is the strongly change. So this type of things we can easily get from here. Or where a strong decrease or slight decrease or a stable or slight increase. So this type of things we can easily get from here for any indices. So in this case we work with NDVI, but same procedure also apply for the NDWI. Not only for that, if you want you can also apply for NDBI. Okay, so you also try for NDBI, basically build up index. You try to make the build up index. You want to identify. So I explain the assignment after some time. First of all I show the result, then you can get the more better idea. So I call the with time and then paste here. And now from this I select the two band. Select the two band. This two band basically time and another for NDVI. Okay, time and NDVI simply choose. And then I apply the linear fit model. So for that use the reduce function. Reduce. How I can reduce? I want to apply the this reducer linear fit. So put here EE dot reducer dot linear fit model. Okay. And now if you check the result, suppose just I print the trend. So from the trend we find out the two output, slope and offset. So if you check from this linear fit, what we can get, two bands, basically two output we find out. Check the scale and offset. Okay, so now we try to identify for scale value and identify where is the strongly decrease of vegetation, where is the strongly increase the vegetation, or strongly decrease the vegetation, or slightly increase the vegetation, or stable or slightly decrease the vegetation. So this type of things we try to identify from the slope, from the scale. Okay, so let's go and try to get the show the result. So for that just take a variable, suppose slope, and call the trend. So from the trend we just choose, we simply select the band of which one, slope, scale. Yeah, so put the scale. Okay, scale, and further we simply dot rename it. Put the rename it, suppose NDVI slope. Okay, NDVI slope, and then clip with our study area. So clip with AOI. So now display the result and check what happened. So map dot add layer and call the slope and run the code. Okay, we find out this type of result, black color. So we try to increase. So I increase, suppose and now I want to add the color. Suppose I want to add, suppose where strongly decrease the vegetation, I want to add, suppose this type of red color. Okay, it's indicating about the strongly decrease. Further we can also make the classification. Okay, strongly decrease, slight decrease, stable decrease, slight increase, and strongly increase we can also identify. So for first time I display, suppose this type of red color, then put here this type of color, and also put this type of green color. Where do we find out the strongly decrease? I put the three color and then apply. So now you just import the visualization and check the map. just copy, paste here, and put here the, it's a NDVI trend, NDVI trend. So now if you check the result, we find out the red color. So this type of red color, vegetation is strongly decreased. If you check, okay, so you can see, we find out, and this result, it show the trend from 1990 to 2025. Between this time period, we find out this type of red color, it's strongly decrease the vegetation, and this type of color, green color, indicating about the strongly increase the vegetation for this type of place. Okay, so if you want, you can also download this map as a GOT file, and further you can also make the class, suppose 5 class or 3 class. Basically in this case, low slope value, it's indicating about that low slope value, it indicating about the decrease, and gradually increasing the slope value, it means that vegetation is also. So you can also make the classification. Suppose you can just simply download this map as a GOT file format, and further we can also work with ArcMap to produce the map. Okay, suppose negative pixel, all of negative slope value, it indicating about the strongly decrease area. Suppose when you just make the analysis, suppose first of all you just simply put strongly decrease, the vegetation, then suppose all of negative pixel. Okay, suppose then we put here the slight decrease, then suppose put here stable, then suppose another class slight increasing the vegetation.